Today let's solve an elevator problem. So this elevator problem isn't really a static equilibrium problem, but it's important to look at because it'll show up on the AP Physics test. So in our problem we have an elevator accelerates upwards at 1.3 meters per second for 3 seconds. Then it has a constant velocity of 4.2 meters per second for 5 seconds. And then it decelerates at 2.1 meters per second for 2 seconds. If you are standing on a scale and your mass is 200 kilograms, what does the scale read in these 3 situations? So let's start at the first one. So for this, we want to use free body diagrams. Looking here, so in our first situation, on our free body diagram, the forces that we have acting on us, we have our weight pulling us down. Yeah, you're kind of a box. And we have the normal force pushing us up. Now we talked about it. The normal force is going to be what your scale is reading. I'm also going to make a note here that in this first situation, we're accelerating upward at 1.3 meters per second squared. Now looking here, if we're accelerating upward because we're going up, that means since the only forces acting on us are our weight pulling down and the normal force, if we're going up with acceleration, our net force must be up. And what that must mean is that our normal force must be bigger than our weight. Again, using Newton's second law, we have that F net, and I guess technically it's in the y direction, equals m_a_y. So looking here, our forces there, well, let's say that for our sign convention, let's have up be positive and down be negative. So then we have that it's our normal force acting up, so it's positive, minus our weight pulling down. And that'll give us our mass times our acceleration. So plugging in, well, I guess ultimately I want to figure out the scale reading, which is our normal force. So that's just going to be my mass times my acceleration in the y direction plus the force due to gravity. So looking here, let's plug in my numbers. Now what do I know? I know my mass is 100. I know that my acceleration is 1.3. And then my force due to gravity is mg. My mass times 9.8, so 100 times 9.8. Put that in my calculator, and I get about 1,110 newtons is what the scale would read. So that's with the first part. And look, I never used the time. That was just an extra piece of information. Now let's look at the second part. For this one, I'm moving at a constant velocity of 2.5 meters per second for 5 seconds. So to draw my free body diagram again, I have my weight pulling us down, and I have the normal force pushing up. For my signs, I'm going to say, again, up is positive, down is negative, because that just makes a little more sense. That's the way we typically think about it. Well, on this one, I have that my velocity is 4.2 meters per second. If I'm moving at a constant velocity, what would my acceleration be? If I'm just moving, my acceleration is going to be 0, right? If I'm moving at a constant velocity. So that means that my net force is going to be 0, and that must mean that my normal force and my weight are the same. So here Fn is the same as mg, or my force due to gravity, my weight. over here when we were accelerating, oops, sorry about that. Let me fix this, hang on. Now that we're back centered, over here we saw that our normal was bigger than our weight when we were accelerating upward. Here, when we're moving at a constant velocity, we see that it's the same. So let's look and calculate that out. So that means F net in our y direction equals mass times acceleration in our y direction. Well, our net forces, we have the normal force minus the force due to gravity, and that'll equal my mass times my acceleration in the y direction. Well, my normal force, let's see, we said that Fn minus my weight mg equals m times O. We said our acceleration is 0. So this will simplify to my normal force is equal to m times g, right, if I just add that over. And that is 100 times 9.8 or 980 newtons. Now we have one more situation left. On this one, we're decelerating at 2.1 meters per second for 2 seconds. So to draw that free body diagram, again, I've got my weight acting on me, and I have the normal force. I'm going to make a note over here that I'm accelerating downward at 2.1 meters per second squared. But I'm still going to say that my sign convention, that up is positive and down is negative, because that's the way that makes sense. And ultimately I want Fn, and so I want that normal force to be positive. So on this one, if over here, when we're accelerating up, we have the normal bigger, now that we're accelerating down, we'd expect the normal to be smaller than the force due to gravity, or mg. And that makes some sense, right? In order for us to be accelerating downward, our net force has to be downward, which means that mg, or force due to gravity, must be smaller than our normal force. So looking here, let's go through our problem solving steps. So we know that the net force in the y direction is equal to mass times acceleration in the y. Well, our forces, we have the normal force acting up, and I said that was the positive direction, minus my weight pulling down, and that is equal to mass times my acceleration of O down, so my acceleration is negative 2.1. Did you guys see that? So because the acceleration is down, and that's my sign convention, the acceleration plugs in negative. So I have Fn equals 100 times negative 2.1 plus, if I move this over, Fg, which is mg, so 100 times 9.8. Plug this in, and I end up with 980 minus 210, or 770 newtons, which is less than my weight and what I'd expect. So that's how to solve an elevator problem. If you note, I did not use any of these times. That was just to trick you. Don't let it trick you on your test. And we can see again that when we were accelerating upward, Fn was bigger than mg. When we had no acceleration, they were balanced. And when we were accelerating downwards, our normal force was smaller.